Okay, this is lecture 2. In this lecture, we will discuss the design of a singly reinforced beam in flexure. What is a singly reinforced section or singly reinforced beam? So, as I told you in lecture 1 that reinforcement is given in RC beam primarily to enhance the tensile capacity of the beam. So, wherever there will be tensile stresses, the part of the section where there will be tensile stresses under the given loading, so we will provide reinforcement in those regions to enhance the capacity of reinforced concrete beam. Like for example, if this is a simply supported beam, okay, and it is subjected to transverse loading, for example uniform distributed loading, or for example point loading, so you know that there will be compressive stresses in the top and tensile stresses will be produced in the bottom. This you know very well. Clear? So what you will do, since you know that concrete is very good in compression but it is weak in tension, so what you can do, you will provide the reinforcement in the bottom fibers of simply reinforced beam like this. Okay, so after the cracks, what will happen, all the tensile stresses will be taken by the steel and the compressive stresses will be taken by the concrete, so it will act in a composite way to resist the given demand. Clear? Is it clear to you?
Yes, sir.
Yes, sir.
If we take a section of this beam, so its section will look like this. This is normally a section of reinforced concrete beam in which reinforcement is provided in the tensile zone. Okay, but you know that of course there will be stirrups in the beam which will basically take care of the shear forces. So the design of these stirrups, it will come from the shear design. Like for example, the dia and the spacing of these stirrups will be calculated from the shear design. This we will discuss in the coming lectures. And also there will be at least two number of bars, in the top of the section to hold these stirrups. So these bars, they are not coming from the analysis, they are not calculated from the analysis of reinforced concrete beam, but they are just provided to hold these stirrups. Okay, so this is a typical singly reinforced concrete section. A typical singly reinforced concrete section or a simply supported beam. So normally, since this is a singly reinforced concrete beam, so normally we will ignore, just for clarity, we will not draw these strips and these two bars. Normally a singly reinforced beam section is drawn like this. This is concrete section and these are tensile reinforcement provided in the beam. Okay, but of course you should know that there will be stirrups and also there will be at least two number of bars in the top to hold these stirrups. Clear?
Yes, sir.
However, in this lecture, we will discuss that how these reinforcement how we will calculate uh, the reinforcement in the tensile portion of the beam. Clear? How to calculate this tensile reinforcement? This we will discuss in this lecture. Okay. Okay. If we have, for example, a beam which is fixed at both ends, fixed supported beam. For example, there is a beam which is fixed at both ends. So for a fixed supported beam, you know that the bending moment diagram will be like this. There will be positive moment at the midspan and negative moment at the ends. So if we take a section at the end, so कोई बता सकता है where will be tensile stresses in the section, in the top or bottom at the end?
In the top, sir.
In the top. Why? Because there is negative moment now, and due to negative moment there will be tensile stresses in the top and compressive stresses in the bottom, unlike the positive bending moment where there will be tensile stresses in the bottom and compressive stresses in the top. So if we take a section, for example section BB, okay, so it will look like this. There will be tensile reinforcement in the top now, and of course there will be stirrups in the beam, and there will be minimum 2 number of bars to hold these stirrups in the compression zone. Okay, so this is mid section, mid of the beam section taken, and this is section taken at the end of the beam. Is it clear to you? So in this case, we will provide reinforcement in the bottom, like for example here, reinforcement is provided in the bottom, as well as at the ends we will also provide reinforcement in the top, like this. Up to how much extent we should provide these top reinforcement? So this will be provided up to this contraflexure point, beyond which the negative bending moment will change into the positive bending moment. Clear?
Yes, sir.
अच्छा, इसके साथ साथ ये एक टर्मिनोलॉजी भी इसके साथ याद रखें, because this will be used in the mechanics of reinforced concrete section. For example, this is a reinforced concrete, singly reinforced concrete beam. So and these are the stirrups provided these are the bars inside the enforcing bars provided in the singly reinforced concrete section. So one is called the total depth of the beam, which is represented by H, and you know that the width of beam is represented by B or BW. Okay, and there is another terminology, there is another parameter which is known as effective depth, which is basically the distance of distance between the extreme compression fiber up to the centroid of tensile reinforcement. This is known as effective depth or D. Effective depth is the distance between the extreme compression fiber up to the centroid of tensile reinforcement. अच्छा, यहाँ तक तो आप समझ गए ना? हेलो, आवाज आ रही है?
जी सर।
जी सर आ रही।
अच्छा, इफेक्टिव डेप्थ का समझ गए कि नहीं?
यस सर।
अच्छा, ये जो क्लियर कवर है, क्लियर कवर ऑन ऑल साइड्स ऑफ द बीम, this is basically 1.5 inch. So it depends on the type of structural member. For different structural member, the value of clear cover will be different. For example, for beam and column, this clear cover is 1.5 inches. For slab, it will be equal to 2.75 inches. And for footing, it will be equal to the clear cover to reinforcement will be 3 inches. Clear? So in case of beam, the clear cover is 1.5 inches. So how to calculate this distance? For example, this distance is denoted by DC. So your H, your D, effective depth will be equal to H minus DC. Now this DC is equal to 1.5 inch, which is the clear cover, plus dia of the stirrup. So dia of the stirrup and plus half dia of this longitudinal bar, which we have provided as a tensile reinforcement. बात समझ में आ रही है कि नहीं? ये पॉइंट
यस
समझ गए?
सर। सर ये इफेक्टिव डेप्थ थोड़ा बता दें कि इसकी क्या कैरेक्टरिस्टिक्स होती है?
क्या?
इफेक्टिव डेप्थ की सर, ये इसकी क्या कैरेक्टरिस्टिक्स होती है?
हाँ, इफेक्टिव डेप्थ असल में जो हम कैलकुलेशन करते हैं, इट विल बी बेस्ड ऑन mainly effective depth, because we assume that in the tensile portion of the beam all the stresses will be taken by the steel, and the steel will resist those stresses at its centroid. Okay, so the couple C and T, which we will discuss later on, will basically will be based on this effective depth D. Clear है?
यस सर।
So this you can calculate if the reinforcement is given. If the die of stirrup, you know, usually the stirrup dia is number 3 bar, so the dia will be equal to 3 by 8 inches, and the main reinforcement, this will be either given to you, okay, or you will calculate this reinforcement. So for the analysis of an existing RC beam, you will know the dia of stirrup and the dia of longitudinal bar. However, for the design of a beam, design of an RC beam, since you will calculate this reinforcement, the longitudinal reinforcement, so therefore in the start you don't know the dia of longitudinal reinforcement. Okay, so what you can do in the start, you can assume that DC is equal to 2.5 inches. Okay, so for example, if your H is equal to 18 inches, depth of beam is 18 inches, so from this you can calculate the effective depth by this 18 minus 2.5 inches, so it will be equal to 15.5 inches. Or if the die of stirrup is known to you and die of longitudinal bar is known to you, so then exactly you can calculate this DC from this equation, and subtracting this DC from H, you will calculate the effective depth D. ये बात समझ गए कि नहीं? हेलो,
यस सर।
इसमें कोई कंफ्यूजन हो तो आप पूछिए, शाबाश। अच्छा, इस केस में डी कोई बता सकता है? डी कौन सा होगा? ये आपके पास डी है या आपके पास ये डी है? इसमें कौन सा डी है?
सर वो सेकंड वाला।
राइट और लेफ्ट?
राइट वाला।
Right one. Why? Because we defined D as distance from the extreme compression fiber. So in this case, the extreme compression fiber is this one, the lower portion. So distance from extreme compression fiber to the centroid of tensile reinforcement. And in this case, you know that the tensile reinforcement is given in the top portion of the beam. Clear? So that is why in this case, this will be your D.
Yes, sir.
So this is basically, these are the two important parameters, for example H and effective depth D, which will be used basically in the reinforced concrete mechanics analysis of a reinforced concrete beam. So that is why I discussed these two parameters in detail. Clear? Now in this lecture we will discuss these topics. These topics will be addressed: behavior of RC beam under gravity load, then its mechanics, ACI code recommendations, design steps, and finally an example. These are the objectives. This is how a reinforced concrete frame will behave when it is subjected to gravity loading. Again, you can see if you closely watch this animation. So this beam, you can see this is divided in small elements. For example, these are small elements of which this beam is made. If you closely see this, you take this one, this element, so you can see at the center of the beam, for example this element, exactly at the center of the beam, so you can see there is elongation. The element is elongated in the bottom, which indicates tensile stresses, and it is contracted in the top, which indicates the compressive stresses. So at the mid section there will be compressive stresses in the top and tensile stresses in the bottom. However, if you take a close look of this element at the end of the beam, so you can say this element is elongated in the top and it is contracted or compressed in the bottom, which means that at the end there will be tensile stresses in the top and compressive stresses in the bottom, which we have already discussed, that at the mid section the tensile reinforcement will be given in the bottom, and at the end section the tensile reinforcement will be given in the top. Okay.
Yes, sir.
Now if we design a beam as per the ACI 318, and if we test that beam, how the beam will behave how the beam will respond to the load. So in order to clearly understand the behavior of RC members subjected to flexure load only, the response of such members at 3 different loading stages will be discussed. But before that, we will show you a video, a beam test video. Basically, there will be a reinforced concrete beam which is designed as per ACI 318, and you will see that how the beam will respond, how the beam will behave when subjected to the increasing load. Okay, this is a video. You should carefully watch this video. माइक किसका ऑन है, ये ऑफ करे जरा. So these are the parameters of the given beam. Depth of beam is 12 inches, width of beam 18 inches, length of the beam is given, it is 7 feet. Bars given as a tensile reinforcement, so number 4 bars are given in the tensile region in the bottom of the beam. Stir spacing is 5 inches, and the maximum calculated capacity is 90 kilonewton for the beam, which means that the beam can take maximum load of 90 kilonewton. Clear? Now you can see this is different views of the tested beam, and the increment of load is 5 kilonewton, so which means that the load is applied at an increment of 5 kilonewton. This is the dial gauge which shows the deflection of beam at the center, and a point load is applied at the center of the beam. You can see the load deflection curve here. At the same time, also the cracks are marked with the corresponding load. For example, the load at which this crack will appear is also marked here. So this first crack, you can see it will come on a load of 30 kilonewton. Okay. So the cracks and the corresponding loads are marked on the beam. Now, since it is an RC section, it is designed as per ACI 318. So you can see after the appearance of the first crack, other cracks will also form at the mid portion of the beam. The number of cracks will increase. So for a well-designed beam, the cracks will always be distributed like this. So you can see each crack, and you can see this in the load deflection curve. After the appearance of the crack at 30 kilonewton, you can see the slope is getting mild. So before the appearance of the crack, the stiffness of the beam is more as compared to the stiffness of the beam after the crack, which you can observe from the slope of load deflection curve. So each crack and the corresponding load at which this crack appears is marked on the beam. Cracks are propagating toward the top. These are the cracks corresponding to 88 kilonewton. Now this zero slope you can see in the load deflection curve. This represents the yielding of tensile reinforcement. Okay, so at this stage the tensile reinforcement has been yielded, and after this the cracks will get widened. Now this crack is corresponding to 105 kilonewton. In the start you have seen that the calculated maximum capacity of this beam is 90 kilonewton, but from experiment you can see that it can go up to 95 kilonewton. It can take the load up to 95 up to 105 kilonewton. Even it is 115 kilonewton. But after this, what will happen? The concrete in the top fibers will get crushed. You can see the crushing of concrete in the top, in the vicinity of the load. And after this, the beam will not take any further load, and the beam is considered as failed. So now, what did you conclude from this video? Anyone? आवाज आ रही है आप लोगों को? Conclusions
Yes, sir.
drawn from this video. What are the important conclusions which can be drawn from this video? One by one, शाबाश.
सर पहले टेंसाइल स्ट्रेसेस जो थे वो हो जाते हैं नीचे, फिर वो आहिस्ता आहिस्ता ऊपर आते हैं, आखिर में सर कंप्रेशन फेलियर हो जाते हैं, तो आखिर में जिसकी वजह से वो बीम की फेलियर हो जाती है कम्प्लीटली.
Okay, anyone else?
यस सर, जैसे हम ये अखज़ कर सकते हैं ना कि टेंसाइल स्ट्रेसेस आर मोर देन द कंप्रेसिव, मतलब कि उसकी शुरुआत पहले से होती है ना, लिहाजा हम जो रिइंफोर्समेंट करते हैं वो टेंसाइल एरिया में जहाँ पे क्रैक बिलो एरिया से नीच एरिया से शुरू हो जाते हैं वहाँ पे रिइंफोर्समेंट करेंगे। और इस एरिया के नज़दीक जहाँ से क्रैक शुरू होते हैं जैसे कि नीचे से यहाँ पे तो टेंसाइल है, लिहाजा वो स्ट्रेस यहाँ पे ज़्यादा है, लिहाजा हम रिइंफोर्समेंट नीचे एरिया में टेस्ट करेंगे।
जी, anyone else? बताए जो भी हो, आपके दिमाग में जो भी आता हो बस आप बताएं। Actually, we can draw 3 or 4 important conclusions from this video. First of all, you can see that at a small loading, or even if there was no load applied on the beam, so you can see the beam was intact, there were no cracks in the beam. As we apply the loading on the beam, so you know that for this beam there will be compressive stresses in the top and tensile stresses in the bottom. This you know from mechanics. Now what will happen as we increase the load, the magnitude of these stresses, tensile stresses and compressive stresses, will increase, and at a certain loading, for example in this case a 30 kilonewton, when the tensile stresses in the bottom exceeds the tensile strength of the concrete, what will happen? A crack will appear at the bottom. बात समझ में आ रही है?
Yes sir.
A crack will appear in the bottom, and after the appearance of the crack, the tensile stresses will be taken by the steel. The reinforcement will get activated and the tensile stresses will be taken by the steel. So the crack will be arrested by the tensile reinforcement, and that is why other cracks will start forming, start appearing at increasing load. So you have seen the video that the number of cracks will be increased by increasing the load on the beam. Clear? If there was no reinforcement at this stage, for example at 30 kilonewton, so what would happen? At 30 kilonewton, if the first crack appeared, so there would be abrupt failure of the beam. The beam would have broken into 2 pieces. That one crack would have propagated toward the top, it would have got widened, and the beam would have broken into 2 pieces if there was no reinforcement. Clear? However, since there is reinforcement, it is a reinforced concrete beam, there is reinforcement in the tensile region of the beam. So what happens? Soon after the appearance of the first crack, the reinforcement will get activated. It will arrest the crack, and after with the increasing load, the number of cracks will increase in the middle portion of the beam. Clear? यहाँ तक समझ गए? यानी फॉर एग्जाम्पल अगर ये अगर प्लेन कंक्रीट होता तो क्या होता, ये जो आपके पास फर्स्ट क्रैक एट 30 किलो न्यूटन अपीयर हुई, तो बस यही क्रैक it would have propagated toward the top, और इसी लोड पर ही बीम फेल हो जाता. क्लियर?
यस सर.
अच्छा, अब इसके बाद आप देखें, after the appearance of the crack of the first crack, you can see that you can see in the load deflection curve that the stiffness of beam will be reduced, but the beam is still able to take the load. The number of cracks will increase, but the beam is taking the load. It is taking the increasing load. इसका क्या मतलब है? इसका मतलब ये है that cracking doesn't indicate failure of the beam. This is important conclusion, very important conclusion. Since you can see in the video that even after the cracks, the beam is still able to take the load, take the increasing load. Okay, so what does it mean? It means that cracking doesn't indicate the failure of the beam. For example, if you see cracks in the beam, it doesn't mean that the beam is failed. Acha. Then you can see at a certain loading, you can see here there will be yielding of tensile reinforcement, which is depicted here in the load deflection curve. So after the yielding of reinforcement, what will happen? It will be followed by the widening of cracks. But even after the yielding of reinforcement, the beam is still able to take here in the load deflection curve, which also means that yielding also doesn't indicate the failure of the beam. Even after yielding of tensile reinforcement, the beam is taking load. Okay, so it means that the cracking of concrete and yielding of tensile reinforcement in a reinforced concrete beam doesn't indicate the failure of the beam. Clear? However, at the last stage, when the concrete in the compression zone got crushed, you can see here, after this you can see the beam is not able to take the load, to take the increasing load, which means that the beam is considered as failed when the concrete in the compression zone crushes. So these are the three important conclusions which can be drawn from this video. First of all, cracking of concrete doesn't indicate failure of the beam. Yielding of reinforcement also doesn't indicate the failure of the beam. The beam will be considered as failed when the concrete in the compression zone crushes. Clear?
एक्सक्यूज मी सर.
जी जी.
सर ये जो रिइंफोर्समेंट हम टेंसाइल स्ट्रेसेस या स्ट्रेंथ के लिए डालते हैं ना, इस तरह अगर हम कंप्रेसिव मेंबर ठाप पे प्रोवाइड करें तो उसकी स्ट्रेंथ और भी बढ़ जाएगी.
हाँ बिल्कुल, वो तो अगर आप एक कंप्रेशन, क्योंकि दिस इज हाई स्ट्रेंथ मटेरियल ना, ये तो बिल्कुल सिंपल है. द रीइंफोर्समेंट इज स्ट्रॉन्गर देन द कंक्रीट. अगर हम गेट फुट स्टील भी ले लें तो इसकी स्ट्रेंथ भी 40 KSI है, जबकि कंक्रीट की स्ट्रेंथ almost normally 3 KSI to 4, 5 और इवन 6 KSI अगर हम ले लें तो ये तो काफ़ी कम है एज कंपेयर टू द स्ट्रेंथ ऑफ द स्टील. तो कंप्रेशन कैपेसिटी भी आप बढ़ा सकते हैं यूजिंग द स्टील, बट प्राइमरीली जो हमने स्टार्ट में इन द फर्स्ट लेक्चर भी डिस्कस किया था, reinforcement is primarily used, primarily का मतलब है कि यानी हम कंप्रेशन कैपेसिटी भी इससे बढ़ा सकते हैं, बट प्राइमरीली वी विल प्रोवाइड दिस टू इन द टेंसाइल रीजन्स ऑफ द स्ट्रक्चर मेंबर। क्लियर? ये बात समझ गए कि नहीं?
यस सर, ये बात समझ आ गई है, लेकिन मैं ये बात कर रहा हूँ कि ये जो टेंसाइल स्ट्रेसेस के लिए हम स्टील प्रोवाइड करते हैं ना, इस तरह
हाँ
अगर टेंसाइल तो प्रोवाइड करते हैं ना, वो तो ऑलरेडी हमने प्रोवाइड किए, लेकिन अगर ये जो हम कंप्रेशन रीजन में हम कंप्रेसिव मेंबर प्रोवाइड करें स्टील या कोई और स्ट्रॉन्गर
इन द
देन
कंप्रेशन
दैट इज,
जोन आप
या इन द
ये
कंप्रेशन।
ये आप ये बताना चाहते हैं कि कंप्रेशन जोन में भी हम प्रोवाइड कर सकते हैं टू इम्प्रूव द कंप्रेशन कैपेसिटी, इस तरह आप बात कर रहे हैं?
यस सर, लेकिन स्टील नहीं, कोई और कंप्रेसिव मेंबर जो यहाँ पे कंप्रेशन को अपोज करे।
हाँ बिल्कुल कर सकते हैं, मगर या तो हम सिंगली रिइंफोर्स बीम डिस्कस कर रहे हैं ना। इन सिंगली रिइंफोर्स बीम सेक्शन इन द वेरी स्टार्ट I told you the definition of singly reinforced concrete section, that it is a section or it is a beam in which the reinforcement is provided only in the tensile region of the beam. Clear?
ओके सर,
बाकी
थैंक
कंप्रेशन कैपेसिटी को तो आप इवन स्टील से भी बढ़ा सकते हैं। आप डबल रिइंफोर्स्ड बीम में फिर हम ये पढ़ेंगे डिटेल के साथ कि हाउ टू इम्प्रूव द कंप्रेशन कैपेसिटी ऑफ द बीम, तो उसके लिए फिर आप इवन स्टील को भी प्रोवाइड कर सकते हैं इन द टॉप। However, since we are discussing here the analysis of singly reinforced concrete section, so that is why in this beam the reinforcement will be only provided in the tensile portion, that is in the bottom in this case. तो ये समझ गए ये चीजें?
यस सर।
इसमें कोई क्वेश्चन हो, कोई कंफ्यूजन हो तो आप पूछें। So for a well designed reinforced concrete beam, what will happen? The number of cracks will increase by increasing the load, and after the cracking the reinforcement will yield. After the yielding of reinforcement, it will be followed by the widening of cracks, and after that there will be crushing of concrete in the compression zone, which is basically considered as the failure of the beam. So the steel in a well-designed beam, the tensile reinforcement would have yielded well before the crushing of concrete in the compression zone. बात समझ में आ रही है?
Yes, sir.
And I told you in the previous lecture, in lecture 1, that at which strain we can assume that the concrete is crushed. Do you remember the value? Crushing strain.
Sir, 0.03.
0.003. Practically it will be different from this value, it will be somewhat closer to this value, but ACI code recommends that you can assume that the crushing strain of concrete is 0.003. So in other words, you can also say that the beam is considered as failed when the compressive strain in the extreme compression fiber reaches at the value of 0.003. बात समझ में आ रही है? From this video you can see that the beam will be considered as failed when the concrete in the compression zone crushes, and it will crush at which strain? SCI code says that you can assume that it will crush at 0.003 strain. Clear? So in other words, you can also say that the beam will be assumed as failed. It will be considered as failed when the strain in the compression zone reaches a value of 0.003. बात समझ में आ रही है?
यस सर।
यस सर।
अच्छा, इसको अगर हम फॉर एग्जांपल डिफरेंट स्टेजेस में, लोडिंग स्टेजेस में अगर हम इसको डिवाइड करें तो देयर आर 3 डिस्टिंक्ट लोडिंग स्टेजेस. One is the loading stage just before the appearance of the first crack. At this stage, just before the appearance of the first crack, what will happen? What will be the distribution of strains and stresses in the concrete? So you know that before the appearance of the crack, there will be linear distribution of stresses and strain in the concrete, in the reinforced concrete section. यहाँ तक clear है ना? And just before the crack, you can assume that the section, the reinforced concrete section, both the concrete in the tensile portion as well as in the compression region will be considered as elastic because there is no crack, and steel in the tensile portion can also be considered as elastic. Clear? So this is the first stage just before the appearance of the first crack, which is basically the elastic stage. After the cracks appear, for example, this stage, you can see there are, as I told you, that after the appearance of the crack, the stresses, the tensile stresses will be taken by the steel. However, the stresses in the tensile steel as well as the compressive stress in the concrete, both will be in the elastic range. So this is another stage in which the compressive stresses in the top fiber and the tensile stresses in the tensile reinforcement, they will be in the elastic range. So this second stage is known as cracked but elastic stage. Crack का मतलब ये कि there will be cracks in the bottom, but the tensile reinforcement will be in the elastic stage. बात समझ में आ रही है कि नहीं?
Yes, sir.
And then there is a final stage in which you can see that the concrete in the top fibers or in the compression zone is crushed. This is the ultimate stage or the failure stage, for which we will basically design the beam. So we will basically derive the flexure capacity of the beam at these different loading stages. Clear? At cracking stage and at the second stage and then at the final stage. So we will apply the reinforced concrete mechanics to derive the flexure capacity at these different loading stages. This is the first stage, which is uncracked concrete stage, which is also an elastic stage. At loads much lower than the ultimate, concrete remains uncracked in compression as well as in tension, and the behavior of steel and concrete both is elastic. Clear? Crack, concrete, and elastic stage. With increasing load, concrete cracks in tension but remains uncracked in compression. Concrete in compression and steel in tension both behave in elastic manner. There are cracks in the tensile portion, but the steel in the tensile region and the concrete in the compression region both are in the elastic range. However, this is the final stage at which both, that is steel in the tensile region and concrete in the compression zone, both have entered into the inelastic stage. You know that at this stage the reinforcement would have already yielded. Now, for example, if we derive the flexure capacity or the resisting moment, the resisting moment capacity of the beam at elastic stage corresponding to the first stage, uncracked stage. Okay, if you remember, I already told you that reinforced concrete member, it is a composite section which is made up of concrete as well as reinforcement, and soon after the load application, it will get into the non-linear stage, because you have seen in the video at loads much lower than the ultimate load, the cracks will appear in the tensile portion of the beam. So after the cracks, the beam will enter into the inelastic stage. Clear? So the equations which we have derived in your mechanics courses, for example, the equation used for the flexure stresses, this flexure formula, this equation is valid for homogeneous beam, homogeneous elastic beam, for a beam which is basically homogeneous and elastic. Clear? अगर आपको याद हो इस ड्यूरेशन में आपने काफी assumption पढ़े, one of the most important assumption was that the section will be homogeneous elastic. Okay, so at the first stage you can consider the beam, the reinforced concrete beam, as a homogeneous elastic, because there are no cracks in the beam and the reinforcement in the beam is not activated at this stage. So you can consider that at this stage the beam behave as a homogeneous elastic section. So at this stage you can apply this equation to derive the flexure strength of the reinforced concrete section. Clear? From this equation, you can derive the resisting moment capacity of the beam, which will be equal to Fr into I divided by C. Clear? Where Fr is the tensile strength of the concrete, and you can calculate this Fr from this empirical equation which we have discussed in the previous lecture. आप लोगों को आवाज आ रही है?
Yes, sir.
So from this you can calculate the moment capacity, the flexure capacity of the beam at this stage. It is very simple. I is equal to BH cube divided by 12 and C is equal to H by 2. Putting all these values in this equation, you will get MR is equal to FR into BH square divided by 6. Or it will be equal to MR is equal to 7.5 under root FC prime into BH square divided by 6. So this is the equation for calculating the flexure capacity of a reinforced concrete section just prior to the appearance of the first crack, when the section is at the verge of the cracking. Clear? However, this equation, this is not valid for the other stages. That is, when, for example, the crack appear in the beam, then you cannot use this equation for calculating the flexure capacity of the beam, because as I told you that this equation is valid for homogeneous elastic section of the beam. Clear? After the appearance of the crack, you can see that the section will act as in a composite way, such that the tensile stresses will be taken by the steel and the compressive stresses will be taken by the concrete. So since the section is a composite section, it is not homogeneous section, and also there will be cracks in the bottom. It will be in the inelastic stage. So therefore, for the other stages, you cannot apply this equation to calculate the flexure capacity of the section. However, using the equilibrium equation, you can calculate the flexure capacity of the beam at this stage as well as at the other stages, because equilibrium will be there at any stage. So we can derive the same flexure capacity equation using the equilibrium equation. So for example, even for the first stage, if for example this is the reinforced concrete beam section, we can apply the equilibrium equation. This is the stress strain, this is the strain diagram. You can see that there will be compressive stress in the bottom, tensile strains in the bottom and compressive strain in the top. And since you know that there will be linear variation, the strains will be proportional to stresses at this stage. So therefore the stresses, this is the stress diagram, stresses in the top and stresses in the bottom. Now from these stresses you can also calculate the compressive as well as the tensile force. This is the compressive force and this is the tensile force. How can you calculate this part of the beam is under the compression? अच्छा, ये मुझे जरा बताइए how to calculate the forces, for example compressive force or tensile force from the respective stresses. तो ये बता सकते हैं compressive force for example हम कैसे calculate कर सकते हैं from the given stress diagram?
area of the compression region.
Area multiplied by
the moment arm.
ये तो बिल्कुल सिंपल है. Stress is equal to force divided by area. इस तरह है कि नहीं? तो force is equal to stress multiplied by area. Clear? So for example, if we want to calculate C, so C will be equal to stresses. Now since you can see that stress is varying linearly, it is 0 at the neutral axis and maximum at the top. So you can take the average stress, which will be equal to Fc plus 0 divided by 2 multiplied by the area on which the stress is acting. What is the area? If this is, for example, B, area on which the stress is acting. Quickly, Shabash.
BH by 2.
It is equal to BH divided by 2. So C is equal to FC, अगर ये हम simplify करें, into BH divided by 4. Similarly, you can also derive the same way T, which is equal to FR plus 0 Why we are taking FR? Because it is at the verge of the breaking. 2 multiplied by BH by 2, which will be equal to FR into BH divided by 4. Now, from this you can also calculate the resisting moment capacity, MR, which will be equal to tensile force multiplied by the lever arm. Why we are taking the tensile force? Because the capacity at this stage is controlled by the tensile force, by this FR. Clear? And multiplied by this lever arm. अच्छा, ये लीवर आर्म किसके बराबर होगा, कोई बता सकता है?
H minus H by 3.
T की वैल्यू तो हम यहाँ से पुट करेंगे. It will be equal to FR into BH divided by 4. अच्छा, ये जरा बताए शाबाश. पहले ये बताए कि ये
H minus H by 3.
ये जरा बताए, ये जो मैंने अभी
2H by 3. 2H by 6 is it?
ये 2H by 6 होगा. 2H divided by 6. और इसी तरीके से ये अगर आप इसके साथ ऐड करें, so these are both are equal. Again it will be equal to 2H by 6. ये दोनों अगर आप ऐड करें, so it will be equal to 2H by 3. Clear है?
Yes, sir.
So this will be equal to 2H divided by 3. इसको अगर हम सिंप्लीफाई करें, so this will be cancelled with this, and finally MR will be equal to FR into BH square divided by 6. You can also write this. MR is equal to FR is equal to 7.5 under root FC prime into BH square divided by 6. अब इस इक्वेशन को देखें, it is exactly the same which we have derived on this slide. But now in this case we have derived the same equation for the resisting moment capacity by applying the equilibrium equation. Okay, and you can use the same technique, that is applying the equilibrium equation at any stage at any stage to calculate the flexure capacity, because equilibrium will be there at any stage. Clear?
Yes, sir.
So that is why I derived the same flexure capacity equation using the equilibrium equation, because for the other stages the flexure formula will not be valid. So using this technique you will derive basically the relation for calculating the flexure capacity of reinforced concrete section. So at the cracking stage, just prior to the appearance of the first crack, the flexure capacity of reinforced concrete section is equal to how much? 7.5 under root fc prime into b square divided by 6. From this you can calculate the flexure capacity of reinforced concrete section. यहाँ तक क्लियर है? Any question? रिस्पॉन्ड करें ना यार.
यस सर, क्लियर है.
ओके. अच्छा, यहाँ पर आप स्टील की जो कंट्रीब्यूशन है हम इग्नोर करते हैं, बिकॉज दैट the capacity which is coming from the steel reinforcement which is provided in the beam is very small, so that is why we can ignore the contribution of reinforcement in the flexure capacity of the beam at this stage. इसी स्टेज पर हम उसको इग्नोर कर सकते हैं. सही. However, if you want to aid the contribution of flexure reinforcement, so you can also add the contribution of flexure reinforcement in the capacity at this stage, and that is very simple. यहाँ पर आप देखें, you can calculate the strain at this location from strain compatibility from similarity of triangle. You can calculate the strain in the steel. If this will be equal to strain in the steel. This you can derive, this you can calculate from similarity of triangle. Okay. Again, if we ignore the effect of reinforcement on the depth of the neutral axis, अगर हम इसकी इफेक्ट को इग्नोर करें तो उससे हम ये स्ट्रेन कैलकुलेट कर सकते हैं. फॉर एग्जांपल, दिस डिस्टेंस इज h/2 and this strain at FR, it is equal to how much? यहाँ पर मैं दोबारा ज़रा ये कर देता हूँ.
सर 15 मिनट की ब्रेक कर लेते.
नहीं, ब्रेक नहीं करते. सही. The strain at this the extreme tension fiber at this stage, this will be equal to FR divided by E, because you know that at the elastic stage you can calculate the strain from the Hooke's law. Okay, now so this stress value is known to you, which is equal to 7.5 under root FC prime. And also I told you in the previous class that you can calculate the elastic modulus of concrete using the relation 57,000 under root of C prime. From this relation you can calculate the elastic modulus of the concrete. So putting this value here, 57,000 under root of C prime. From this you can calculate the strain at this stage. These are calculate करें शाबाश quickly. तो ये दोनों कैंसिल हो जाएंगे. 7.5 डिवाइड बाई 57,000. ये वैल्यू जरा बताइए शाबाश.
0.0001.
0.0001.
Yes sir.
उसके आगे बताइए जरा. 0.0001. आवाज नहीं आ रही यार.
सॉरी सर, मैंने तो नीचे वाली वैल्यू 75,000 लिखी है
सर. 0.00011316.
बस 0.0013 value is the strain value. Now you know that this distance is equal to h by 2, and this distance I told you that you can assume this distance is 2.5 inches. Clear? या आप कैलकुलेट कर सकते हैं DC. This distance is equal to basically DC, और DC आप कैलकुलेट कर सकते हैं if you know the die of stress and the die of longitudinal reinforcement. बात समझ में आ रही कि नहीं? मगर अगर आप नहीं कैलकुलेट करते तो आप इसको एज्यूम कर सकते हैं as 2.5 inches. क्लियर? यहाँ तक क्लियर है?
Yes sir.
Okay, from this you can calculate the strain in the tensile reinforcement by similarity of triangle, that is equal to E. For example, this is ER, to ER divided by H by 2. For example, if we assume that the depth of the beam is 18 inches and the width of beam is 12 inches. So ER divided by H by 2, which is equal to 9 inches, is equal to EX divided by this distance. Clear? ये distance किसके बराबर होगा?
-9 DC.
9 minus DC are, for example, 2.5 inches. So E is divided by 6.5 inches. Now from this we can calculate E is equal to ER. Now what is the value of ER? 0.00013 multiplied by 6.5 divided by 9. जरा बताएं शाबाश. quickly शाबाश.
Zero point 4444939.
0.444 ये क्या?
0.000095.
95.
Yes, sir.
Okay, this is the strain in the reinforcing bar. Now from this strain you can calculate the stresses in the reinforcing bar. How to calculate the stresses in the reinforcing bar?
Sir,
बता सकते
apply
हैं?
Hooke's law.
जी
Sir, can we apply Hooke's law?
हाँ, exactly, because this is in the elastic stage. So you can apply the Hooke law. So using Hooke law, the stress will be equal to E is multiplied by elastic modulus. E is equal to 0.4095 multiplied by elastic modulus. Elastic modulus की वैल्यू क्या है स्टील के लिए? What is the elastic modulus of steel bar?
Sir, 29,000.
29,000. So what is the value of Fs?
Two
Two
point
point seven two two.
2.72 KSI. This is the stress in reinforcing bar. Now from this stress you can calculate the tensile force, and then again applying the equilibrium equation you can calculate the flexure capacity. So that is very simple. अगर हम इसको contribution को ignore नहीं करते तो again this is the stress diagram. This is the compressive force. This is the tensile force of the concrete, and this is the tensile force resisted by the steel. So tensile force resisted by the concrete and tensile force resisted by the steel. अब बात समझ में आ रही है? Because now we are basically considering the effect of steel. अगर आपके पास ये steel है, this is reinforced concrete member, so you have provided reinforcement. So अब हम इसके इफेक्ट को भी ले रहे हैं. अब इस केस में अगर आप देखें तो in this case now how to calculate the flexure capacity? इस केस में आप फ्लेक्सर कैपेसिटी किस तरह कैलकुलेट करेंगे? TC तो ऑलरेडी हमने कैलकुलेट किया है. इट इज इक्वल टू FR into BH square divided by 6. Sorry, FR into BH by 4. Clear? And what about T is tensile force resisted by the steel. ये किसके बराबर होगा? स्ट्रेस को आपने कैलकुलेट किया ना? स्ट्रेस resisted by
2.72.
जी बताए ना?
Sir, F is
FR 2.72 KSI.
हाँ, it will be equal to Fs multiplied by area of steel. And how to calculate the area of steel? Area of steel will be equal to the number of bars
pi d.
multiplied by area of each bar. इस केस में for example the number of bars are 3, and if we are using number 6 bar for example, so the area of number 6 bar is 0.44. It will be equal to 1.32 inch square. बात समझ में आ रही है? So from this you can calculate the tensile force resisted by the steel. Clear? बात समझ में आ रही है कि नहीं?
Yes, sir.
So now from this you can also calculate the flexure capacity. And in this case now the flexure capacity will be equal to MR is equal to again GC multiplied by LA. Now in this case LA is this one, or we can say that this is LC plus TS multiplied by LS. Lever arm of the reinforcement is denoted by LS, for example. Clear? So now you know the value of this. This is equal to FR into BH square by 6. Already हमने किया है, and plus TS multiplied by LS. So TS is equal to AS into FS multiplied by LS. अच्छा ये किसके बराबर होगा, कोई बता सकता है? LS. LC तो आपको पता है, दिस इज 2/3H. Now what about LS? पहले ये बताए जरा, ये डिस्टेंस किसके बराबर होगा?
H/6.
इज इक्वल टू H/6. और ये डिस्टेंस टोटल यहां से यहां तक, ये डिस्टेंस किसके बराबर है?
DC.
तो इससे आप ये LS कैलकुलेट नहीं कर सकते? अब बताए LS किसके बराबर होगा?
So D minus H/6.
D minus H/6. तो यहाँ पर आप पुट करें LS is equal to D minus H divided by 6. क्लियर? इसका क्या मतलब है? If you are ignoring the effect of reinforcement, then the equation will be equal to FR into B square by 6. And if you want to take the effect of reinforcement, so then you will add just this term with in the equation. बात समझ आ रही है? अब इसके इफेक्ट को जरा देखते हैं, सही? तो इस पर हम अगर एक एग्जांपल करें तो आप लोगों को
सर
जी जी
यहाँ पे डी जो है डेप्थ ऑफ रिइंफोर्समेंट है या क्या चीज है?
अभी तो हमने ऑलरेडी डिस्कस किया है. दिस इज इफेक्टिव डेप्थ,
ओके सर,
which is basically the distance from extreme compression fiber up to the centroid of tensile reinforcement. Clear? ऑलरेडी हमने डिस्कस किया है ना, एट द वेरी फर्स्ट स्लाइड.
सर मैं लेट ऑनलाइन हुआ.
अच्छा, यहाँ पर अगर आप देखें, हम अगर एक एग्जांपल करें, फॉर एग्जांपल दिस इज ए बीम which is 12 inch wide and the total depth of the beam is, for example, 18 inches. Reinforcement is provided in the beam. The effective depth is equal to, okay, if the reinforcement in the beam is, for example, 3 number 6 bars, so can you calculate DC from this? DC will be equal to जल्दी बताए, शाबाश। DC किसके बराबर होगा? .5 inch, which is the clear cover, plus die of stirrup.
0.
Normally it is 3/8, and plus half dia of the longitudinal bar, so half into 3/4. Please जरा बताएं, शाबाश। DC is equal to, quickly शाबाश यार, एडिशन भी आप नहीं कर सकते। Why you are taking so much time यार? सिंपल एडिशन करें ना, इसमें क्या है? ये समझ रहे हैं कि नहीं?
सर 2.25
2.25
जो मैं कर रहा हूँ आप लोग समझ भी रहे कि नहीं?
सर यहाँ पे समझ नहीं यार, डीसी आप कैसे फाइंड करते हैं?
आपने कब ज्वाइन किया है?
सर 8:45 अबाउट।
नहीं, फर्स्ट स्लाइड में आप थे कि नहीं?
नो सर।
ये सिंपल है, यहाँ पर मैंने आपको बताया था कि there will be steps provided here. Okay, this clear cover for beam, it is 1.5 inches, which is provided on all sides, plus dia of stirrup, and plus half dia of the longitudinal bar. This will be equal to DC. अब समझ में आ रही है?
ओके सर, थैंक यू।
So this is equal to 2.25 inches. So now from this you can calculate the effective depth, which is D. D is equal to 18 minus 2.25 inches. ये किसके बराबर होगा? जल्दी जल्दी बताइए, शाबाश।
$15.75.
Clear? And now if C prime in this case is equal to 3 KSI, and Fy is equal to 60 KSI, or for example 40 KSI. So we are using breadfruit steel, and the concrete compressive strength is 3 KSI. These are the geometric and material properties of the section. From this, for example, if we calculate the flexure capacity at stage 1, so flexure capacity in stage 1, if we ignore the contribution of steel, it is equal to 7.5 under root Fc prime B is square divided by 6. 7.5 under root Fc prime is 3000 psi. I told you that whenever Fc prime comes in the square root, so you will use the units of psi. B in this case is 12, H is 18, square divided by 6. Quickly, Shabash, बताएं, what is the value of MR?
$266.19 K dot inch.
266.2 inch thick almost. Clear? And now this is when we ignore the contribution of steel at this stage. Now, if we consider the effect of steel, then it will be equal to 7.5 under root Fc prime B square divided by 6 plus AS into Fs multiplied by D minus H by 6. Clear? Now this we have calculated, it is 266.2 plus A is in this case is equal to 1.32. If is we have already calculated in the previous, यहाँ पर अगर आप देखें यहाँ पर ऑलरेडी हम कैलकुलेट कर चुके हैं 3 इंच डीप बीम के लिए.
Sir, if H
It is
is equal to 2.7.
Yeah. If is in this case is equal to 2.72, 1.32 multiplied by 2.72 and multiplied by D is 15.75 minus H by 6. So 18 by 6 is equal to 3. ये जरा कैलकुलेट करें शाबाश quickly.
After sum total 311.98.
नहीं ये जरा कैलकुलेट करें, ये only this portion.
$45.78.
45.78 inch tip. Okay. So you can see in this case, even if we ignore the effect of steel, so it will give you a reasonably accurate value. Clear? And a 45 inch hip is very less as compared to 266 inch hip. Okay. But if you want to add the effect of steel, then the total moment resisting capacity at this stage will be equal to how much?
311.98.
0.98 inch. Okay.
Okay.
So this is how you can calculate the flexure capacity of the reinforced concrete section at stage 1, ignoring the steel contribution. Also, if you consider the effect of steel contribution, so you can calculate this like this. Okay. Now, how to calculate the flexure capacity of the reinforced concrete section at stage 2? In the stage 2, the concrete in the tensile portion is cracked. However, the concrete in the compression zone and steel in the tensile zone both are behaving elastically. If this is the reinforced concrete section, reinforcement is provided in the tensile portion. Again, this is the strain diagram. The strain diagram will remain the same. However, the stress diagram will be like this. Now, since the concrete in the tensile portion is cracked, so we will assume that all the tensile stresses will be taken by the steel alone, and the compressive stresses will be taken by the concrete. So you can see that the variation of stress and strain remains linear in the compression zone. However, in the tensile zone, you can see that the contribution of concrete is now ignored. In the tensile portion, we ignore the effect of concrete and we assume that all the tensile stresses after the cracking in the beam will be taken by the steel. But
Yes, sir.
अच्छा, so now again using the equilibrium equation, you can calculate the flexure capacity of the section at this stage. Clear? अच्छा, ये जरा मुझे बताएं, कोई बता सकता है depth of neutral axis, for example it is denoted by small c, it will be less than h by 2 or greater than h by 2? Previous case में the depth of neutral axis was equal to h by 2 when we ignore the effect of steel. After the cracking, C will get reduced or it will be increased. कोई बता सकता है?
Sir, I think less than.
Yes, it will be less than
Sir,
h by 2. C will be less than h by 2. And what will be the value of C? तो हम आगे उसके लिए relation develop करते हैं that how to calculate the value of C at this stage. But of course it will be less than h by 2 because now the concrete in the tensile portion is cracked. Clear? ये बात समझ में आ रही है ना सबको?
Yes, sir.
So that is why the neutral axis will shift toward the top because there will be cracks in the bottom. Acha. Now, for example, if we assume that the stresses in the extreme compression fiber is equal to 0.45 Fc prime. If we assume that, because we already discussed about this, that the concrete in the compression zone and steel in the tension zone both will be in the elastic stage. If we assume that the stresses in the extreme compression fiber it is 0.45 Fc prime and stress in the steel is equal to 0.5 Fy, that is half the yield strength, and stress in concrete is also almost half the concrete strength. 0.45 is almost equal to 0.5. So we can calculate the compression force and tensile force using the same relation. Now this compression force is denoted by capital C because the depth of neutral axis is also denoted by C. So can you tell me how to calculate this compression force? Quickly, Shabash.
Compressor stress multiplied by area of the compression unit.
कंप्रेसिव स्ट्रेस किसके बराबर होगा? .45 Fc prime
multiplied by BC
plus
divided by
0 divided by 2 because we will take the average stress.
yes sir.
Multiplied by the area on which the stress is acting. So what is the area?
BC by 2.
BC, not 2. Where from 2 is coming?
Oh sorry sir.
BC. So C will be equal to compressive force will be equal to 0.45 Fc prime into BC divided by 2. This is the compressive force. And what about the tensile force? Quickly, Shabash. जल्दी करें ना. Tensile force.
Zero 0.5 Fy multiplied by the area of the steel.
0.5 Fy multiplied by area of steel. इसमें क्या है? So this is the tensile force. Clear? Now from equilibrium, you know that from summation Fx is equal to 0, we know that C will be equal to T, and C is equal to 0.45 Fc prime into BC divided by 2. T is equal to 0.5 Fy into As. Clear? This will be cancelled out with this, and from this you can calculate the value of C. It will be equal to As into Fy divided by 0.45 Fc prime into B. Now for a given beam with given reinforcement, we can calculate the depth of neutral axis for this stage. जो हमने एग्जांपल की, इस एग्जांपल के लिए अगर हम C को कैलकुलेट करना चाहें, इस एग्जांपल के लिए, तो ये वैल्यू जरा यहाँ पर पुट करें, तो you will get the value of C at this stage. AS was equal to 1.32, Fy is 40, divided by 0.45 multiplied by Fc prime is 3 and B is 12 inches. जरा कैलकुलेट करें C की वैल्यू शाबाश.
3.26 inch.
3.26 inches. So now you can see that it is less than the h by 2, which is equal to 9 inches. समझ
Yes.
क्वालिटेटिवली आपको पहले से पता था कि C will be less than h by 2. So this is the difference between qualitative mechanics and quantitative mechanics. Qualitatively, you knew it that it will be less than h by 2. But how to calculate it quantitatively? For this, you need the quantitative mechanics. Clear? So now you have calculated the value of C is less than h by 2. Clear?
Yes, sir.
Now you can calculate the flexure capacity of the beam at this stage by multiplying T with the lever arm. अब कोई बता सकता है what will be the lever arm? लीवर आर्म की वैल्यू बताइए शाबाश. लीवर आर्म किसके बराबर होगा इस केस में?
D minus C by 3.
Yes, exactly. It will be equal to D because this distance is C by 3 and this total distance is D. So LA is equal to D minus C divided by 3. Clear? तो यहाँ पर आप पुट करें जरा. MR is equal to T multiplied by LA. T is equal to 0.5 Fy into AS multiplied by LA, which is equal to D minus C by 3. So now since you know all these values for the given example, so for the given example you can calculate the flexure capacity at the second stage. So now the flexure capacity at the second stage is equal to, again I am writing the same equation, 0.5 Fy_As into D minus C by 3. अगर इस एग्जाम्पल के लिए हम कैलकुलेट करें तो it will be equal to 0.5 multiplied by, it was equal to 40, As was equal to 1.32 multiplied by D was equal to 15.75 minus C की वैल्यू अभी हमने कैलकुलेट की, इज इक्वल टू 3.26 डिवाइड बाई 3। ये जरा कैलकुलेट करें शाबाश। व्हाट इज द वैल्यू ऑफ प्लग कैपेसिटी?
387.1.
387.112.
387.112 इंच थिक। ये जरा कंफर्म करें दोबारा शाबाश।
यस सर, मेरे साथ भी
Yes sir, यही आ रही है।
So you can see the capacity at second stage is greater than the capacity corresponding to stage 1, which was almost equal to 266 inch thick. बात समझ में आ रही है? Because at stage 1 you are not allowing even the crack in the beam. So of course the capacity corresponding to stage 1 will be less than the capacity corresponding to stage 2. Clear? ये बात समझ में आ रही है कि नहीं?
No sir.
यस सर।
इसमें क्या मसला क्या है? आप बीम के वीडियो में भी देखें ना, at 30 kilonewton there was first crack, and cracks, number of cracks were increased and the load value, it was also increased. At this stage the load value was almost 50 kilonewton. बात समझ में आ रही है ना?
Yes sir, yes sir.
So this is how you can calculate the flexure capacity of the beam corresponding to stage 2. And this stage 2, it is corresponding to working stress approach. If you remember, हमने बिल्कुल फर्स्ट क्लास में वर्किंग स्ट्रेस और स्ट्रेन डिजाइन अप्रोच डिस्कस किए थे। तो this stage is corresponding to working stress approach. If you remember, in working stress approach, we incorporate the factor of safety by dividing the strength of material on 2. तो आप यहाँ पर देखें ना, stress in the steel is Fy by 2 and stress in the concrete is almost Fc prime by 2. You can see that the material strengths have been divided on 2. Okay? यहाँ तक कोई क्वेश्चन हो तो पूछे। Now we will derive the flexure capacity of reinforced concrete section at the failure stage or at the ultimate stage. Clear? Now at the ultimate stage, you know that, for example, this is a reinforced concrete section. This is the strain diagram. However, the stress diagram at this stage this will be, you know, this value will be equal to 0.003, and stress diagram will be like this. Now at this stage, since the concrete has entered into the inelastic stage, so the stress strain relation will no more be linear, and you can see that the stress will vary non-linearly with the strain. Clear? And the steel would have already yielded at this stage, so you know that the stress in the steel will be equal to Fy. So at this stage, strain in the concrete in the extreme compression fiber and stress in the steel is known to you. बात समझ में आ रही है कि नहीं?
Yes, sir.
कोई कंफ्यूजन हो तो आप पूछे ना.
नहीं सही है सर.
सही. अच्छा. So at this stage, the strain in the extreme compression fiber is 0.003 because this is the crushing strain, and since you know that the steel would have already yielded before the crushing, so the stress in concrete, the steel is also known, it is Fy. Clear? Now you can easily calculate the tensile force in the steel resisted by the steel from this equation S into Fy. However, how to calculate the compressive force? Compressive force आप किस तरह कैलकुलेट करेंगे? कोई बता सकता है?
सर स्ट्रेस इनटू एरिया होगा, लेकिन स्ट्रेस के लिए फिर इंटीग्रेट करेंगे 2D कर्व.
हाँ, फर्स्ट ऑफ ऑल आप इस तरह करेंगे कि इस कर्व के लिए ये बेसिकली अगर आप इसको देखें, दिस इज बेसिकली स्ट्रेस स्ट्रेन कर्व ऑफ द कंक्रीट. कंक्रीट टेस्ट आप करते हैं ना, स्ट्रेस स्ट्रेन कर्व इस तरह होता है. या ऑलरेडी हमने लेक्चर 1 में पढ़ा है. दिस वैल्यू इज 0.003 एंड दिस वैल्यू इज 0.002. तो ये भी डिस्ट्रीब्यूशन इज लाइक दिस. तो फर्स्ट ऑफ ऑल इस तरह करेंगे आप, इस कर्व के लिए आप एक इक्वेशन डेवलप करेंगे. नॉर्मली इसके लिए जो इक्वेशन यूज होता है फॉर अनकन्फाइंड कंक्रीट, इट इज इक्वल टू FC इज इक्वल टू FC prime into 2 E divided by E naught minus E divided by E naught square. This is an equation proposed by Hognestad. This is normally used for this curve. क्योंकि आपको पता है up to this point, for example, linear stage, you can calculate the stress in the concrete from the strain, from the corresponding strain using Hooke's law. After this, it will enter into the nonlinear range, and then for this portion of the curve, you cannot calculate stress directly from the strain. So using this relation, you can calculate stresses from the strain at any strain. This E naught is equal to basically 0.002. That is the stress corresponding to the maximum stress of strain. So Now what you will do, you will basically integrate this equation. From integration of this equation or the corresponding area, you can calculate this force. Okay, तो पहले इसको आपने डेवलप करना है, फिर उसको इंटीग्रेट करना है. Then using some other mathematical relations, you will calculate this distance. That how to calculate the centroid of this area, because the C will be resisted on the centroid. तो फिर centroid को किस तरह calculate करेंगे? So it becomes very difficult mathematically. बात समझ में आ रही है? ये सी अगर आप कैलकुलेट करते हैं तो पहले आपने इस रिलेशन को डेवलप करना है, इसको इंटीग्रेट करना है, then using some other mathematical relations, फिर you have to calculate the centroid at which this C will be resisted. So it becomes very difficult from the practical design point of view. So there is another simple way of representing this curve by an equivalent stress block. This can be represented by an equivalent stress block, rectangular stress block, which is proposed by Whitney. So this stress block is also known as Whitney rectangular stress block, which says that in this stress block the stress variation will be uniform, stress will not vary, the average value will be equal to 0.85 FC prime, and the depth of this block will be represented by A, and of course it will be less than C, because C will be equal to from this up to this point. ये कितना कम होगा? तो quote says that A will be equal to beta 1 into C, and beta 1 will be equal to 0.85 for FC prime less than or equal to 4000 psi. Clear? यहाँ तक क्लियर है?
Yes, sir.
Yes, sir.
अच्छा, now if you convert this actual stress diagram, or you replace this actual stress diagram with Whitney stress block, so then the equations become very simple. अब C भी आप बिल्कुल आसानी के साथ कैलकुलेट कर सकते हैं. C will be equal to C किसके बराबर होगा? कंप्रेसिव फोर्स. कोई बता सकता है? शाबाश, क्विकली.
Compressor stress multiplied by area.
So compressive stress in the stress block is equal to 0.85 C prime. It is constant, and multiplied by area on which this stress is acting is equal to this much area. This is A, and this is B to the BA. So compressive force is equal to 0.85 FC prime BA. And now you know very well that the force, compressive force, will be resisted at the centroid of this block, and you can calculate from this very easily the lever arm. Lever arm किसके बराबर होगा?
D minus A by 2.
D minus A by 2. Clear? Now from this relation, you can calculate the depth of the compression block, which will be equal to, no, sorry. First of all, you will calculate T. T is equal to ASFY. It is very easy. And now using equilibrium equation, you know that C will be equal to T. So C is equal to 0.85 FC prime VA. T is equal to ASFY. So from this you can calculate the depth of compression block, which will be equal to ASFY divided by 0.85 FC prime into B. Clear? So for a given beam with given reinforcement, you can calculate the depth of the compression block at the ultimate stage. Clear?
Yes, sir.
Now, you know that resisting moment capacity will be equal to T multiplied by LA. T is equal to ASFY, and LA, you know, it is equal to D minus A by 2. So from this you can calculate the moment capacity at the failure stage or at the ultimate stage. जो एग्जाम्पल हमने किया है, अगर इसके लिए हम कैलकुलेट करें तो फॉर द गिवन एग्जाम्पल जो हम ऑलरेडी डिस्कस कर रहे हैं, उसके लिए AS was how much?
1.3 something.
1.32 multiplied by 40 divided by 0.85 multiplied by FC prime, which is 3, and B is 12. A की वैल्यू जरा बताएं शाबाश क्विकली.
1.73.
1.73 इंचेस. तो इससे आप जरा कैपेसिटी कैलकुलेट करें. इट इज इक्वल टू ASFY into D minus A by 2. AS was equal to 1.32 multiplied by 40. D was equal to 15.75. Sorry, minus A by 2. So A is equal to 1.73 divided by 2. ये जरा बताएं शाबाश.
785.93.
785.93 inches. Now you can see that this capacity is more than the capacity corresponding to stage 2, which is 387. It is greater than 266. Clear?
Yes, sir.
To be quite logical. So this is how you can calculate the flexure capacity of a reinforced concrete section at the ultimate stage. Is there any question?
No, sir.
Question हो तो आप पूछिए शाबाश. And now this is basically the stage, this final stage, ultimate stage. This is corresponding to strength design approach, because in the strength design approach we will design the beam for the ultimate stage. तो आगे हम पढ़ेंगे कि किस तरह इसके लिए हम डिजाइन करते हैं. But I think now you are clear on how to calculate the flexure capacity of the section and how to apply the equilibrium equation at different loading stages. Clear?
Yes, sir.
अच्छा, ये तो रेजिस्टिंग मोमेंट कैपेसिटी है. अप्लाइड मोमेंट कैपेसिटी, अप्लाइड मोमेंट्स वो कहाँ से आएंगे? वो तो डिमांड है जो आपने वीडियो में देखी. The load which we have applied on the beam, that was basically applied moment. Clear?
Yeah.
Any question?
No, sir. It's clear.
No, sir.
अच्छा, अब अगर हम एग्जाम्पल करें एंड इफ यू
Excuse me, sir.
डिजाइन जी
सर 11 बजे नेक्स्ट क्लास है सर, आज के लिए
बिल्कुल
काफी नहीं है सर?
तो फिर एक क्लास अरेंज करेंगे फिर, क्योंकि इस लेक्चर को तो हमने खत्म करना है ना।
सर फिर ठीक है ना सर,
ये
रात को
basics तो
सर
हमने
10
पढ़े
बजे
हैं।
10 बजे
रात को ले लेंगे सर।
10 बजे लेंगे सर।
नहीं, रात को तो खैर अगर नहीं लेते तो थर्सडे 8 AM अगर आप फारिग हैं तो
सर
Thursday को
8
लेंगे
हमारी
class।
क्लास है सर, थर्सडे को सर।
फ्राइडे को फ्री है।
सर आज रात 10 बजे ठीक है सर।
अच्छा तो खैर है, मैं फिर मैसेज करूंगा, आई विल इन्फॉर्म यू थ्रू CR। तो जो भी टाइम
सर
हो मैं
दिन के वक्त
आपको
अरेंज करें, रात के वक्त सर लाइट
बताऊंगा।
नहीं होती सर।
फिर हम एक दिन
सर
के वक्त
तरावी
arrange
पढ़ के
करेंगे।
बंदा सो भी जाता होता है सर फिर।
सही है, बस मैं देखता हूँ ना। आई विल इन्फॉर्म यू थ्रू द CR। क्लियर?
ओके सर।
Now if you have any question you can ask the question, otherwise you can leave the class.
Thank you, sir.
सर अस्सलाम वालेकुम सर।
सर अटेंडेंस होगी?
Any question?